Welcome to this comprehensive guide for beginner C-sharp developers, where we'll explore the powerful utilities of span, T, memory, T, and unsafe in C-sharp. These advanced features are essential for writing highly optimized and efficient C-sharp code, especially when dealing with performance-critical applications. These features, introduced in C-sharp 7.2 and .NET Core 2.1, are crucial for optimizing performance by minimizing memory allocations and copying. They represent a significant evolution in how C-sharp developers can manage and interact with memory, leading to substantial performance gains in various scenarios. Span T and memory T are structs designed to work with contiguous regions of memory safely and efficiently. They provide a modern, type-safe alternative to older methods of memory manipulation, offering both performance and reliability. Span T represents a contiguous block of memory and can be created from arrays, strings, or unmanaged memory, offering high performance for synchronous operations. This means you can work with portions of existing data structures without incurring the overhead of creating new copies, which is a common bottleneck in many applications. Conversely, memory T is similar but heap allocated, making it suitable for asynchronous operations, though with a slight performance trade-off. Its heap allocation allows it to be safely passed across asynchronous boundaries, which is a key distinction from span T and expands its utility in modern, async-heavy applications. These utilities allow you to manipulate data sections without copying them, significantly reducing memory allocations and improving overall application performance. By avoiding unnecessary memory allocations, they also reduce the pressure on the garbage collector, leading to smoother and more responsive applications. They are particularly beneficial when dealing with large datasets, extensive string manipulations, and I/O operations, where memory efficiency is paramount. Imagine processing gigabytes of data or handling high-throughput network streams. Span T and memory T become indispensable tools in such scenarios. Let's delve deeper into span T, a value type that represents a contiguous region of arbitrary memory, whether on the stack, heap, or unmanaged. Its flexibility in referencing different memory locations makes it incredibly powerful for low-level optimizations while maintaining C-sharp S-type safety. As a ref struct, span T has specific limitations. It cannot be boxed, assigned to object or dynamic types, or used across await and yield boundaries. These restrictions are by design, ensuring that span T remains a stack-only type, which is crucial for its performance characteristics and safety guarantees. Creating a span T from an array is straightforward, and any modifications to the span T directly affect the original array. This direct manipulation without copying is a cornerstone of span T's efficiency, allowing for in-place data processing and avoiding redundant memory usage. Slicing a span T creates a new view of the data without allocating new memory, making it incredibly efficient for parsing and tokenizing. This non-allocating slicing capability is a game changer for scenarios like parsing log files or processing network packets, where performance is critical. This efficiency reduces the overhead of creating substrings or subarrays and interacts more favorably with the garbage collector in stack-only scenarios. By minimizing heap allocations, span T helps to reduce garbage collection pauses, contributing to a more consistent and predictable application performance. Now, let's explore memory T, a struct that also represents a contiguous region of memory but is heap allocated. This fundamental difference from span T is what enables its use in a wider range of scenarios, particularly those involving asynchronous operations. This heap allocation is what makes memory T compatible with asynchronous operations, a key distinction from span T. Because memory T is heap allocated, it can safely outlive the stack frame in which it was created, making it suitable for passing data across await boundaries and into background tasks. You can easily create memory T from an array and then obtain a span T from it for synchronous processing. This interoperability allows you to leverage the strengths of both types. Memory T for asynchronous data management and span T for high-performance synchronous processing of that data. Slicing memory T works similarly to span T, providing a new view without additional memory allocation. This consistent slicing behavior across both span T and memory T simplifies data manipulation and reinforces the principle of avoiding unnecessary copies. Its asynchronous compatibility makes memory T ideal for handling large datasets asynchronously, such as reading files or working with network streams. For example, when downloading a large file, memory T can be used to manage the incoming data chunks efficiently without blocking the main thread. Next, we venture into unsafe utilities, which allow direct memory access through pointers, bypassing C# S-type and memory safety checks. While powerful, this capability comes with significant responsibility, as it opens the door to potential memory-related issues if not used carefully. To use unsafe code, you must mark the code block, method, or type with the unsafe keyword and enable it in your project's build settings. This explicit declaration serves as a warning to developers that the code within these sections operates outside the usual safety guarantees of C#. While unsafe code can boost performance by enabling direct memory access and avoiding array-bound checks, it introduces significant risks. The performance gains can be substantial in very specific scenarios, but they must be weighed against the increased complexity and potential for critical bugs. These risks include memory corruption, buffer overflows, and undefined behavior, demanding extreme caution and thorough testing. A single mistake in unsafe code can lead to application crashes, security vulnerabilities, or subtle bugs that are incredibly difficult to diagnose and fix. For Unity developers, enabling unsafe code involves changing the API compatibility level to .NET 2.0 subset and creating a smcs.rsp file with unsafe in your assets directory. This specific setup is necessary to allow the Unity compiler to process unsafe code blocks within your game projects. Restarting Visual Studio and the Unity editor after these changes is essential for them to take effect. This ensures that the development environment correctly recognizes and compiles your unsafe code, preventing compilation errors and allowing you to leverage these advanced features. Unsafe.as is particularly useful when performance is critical, generic specialization is needed, or for low-level interop with native code. It allows for highly optimized type conversions and memory reinterpretations, which can be crucial in scenarios where every CPU cycle counts. In Unity, span T and memory T can be combined with the burst compiler for high-performance code, especially in data-oriented design. This powerful combination allows Unity developers to write highly optimized, cache-friendly code that runs at near-native speeds, significantly boosting game performance. Unsafe code can also be used to interface with native C++ libraries or manage memory outside the garbage collector, offering fine-grained control. This is particularly relevant in game development for integrating third-party libraries or implementing custom memory management schemes for specific performance needs. When considering performance, span T and memory T significantly reduce allocations, while unsafe code offers additional gains in specific, highly optimized scenarios. It's a spectrum of optimization, with span T and memory T providing safe, general-purpose improvements, and unsafe code offering maximum control at increased risk. Always measure the performance impact to ensure these utilities genuinely improve your application, rather than introducing unnecessary complexity. Premature optimization, especially with unsafe code, can lead to more problems than it solves, so profiling is key to making informed decisions. For best practices, use span T for synchronous APIs and memory T for asynchronous ones. This clear separation of concerns leverages the inherent strengths of each type, ensuring both performance and safety in your C# applications. Isolate unsafe code within small, specialized methods. Keep blocks concise, and thoroughly test all memory operations. By encapsulating unsafe logic, you minimize its potential impact and make it easier to review and verify for correctness, reducing the risk of critical bugs. Always include clear comments explaining why unsafe code is necessary and verify types before performing casts with unsafe.as. Documentation and rigorous type checking are vital safeguards when working with direct memory manipulation, helping to prevent errors and improve code maintainability. Finally, span-T is a more versatile and performant alternative to the older array segment T, supporting both managed and unmanaged memory. Its broader applicability and superior performance make it the preferred choice for modern C# development when dealing with contiguous memory regions. Thank you for joining us in this deep dive into span-T, memory-T, and unsafe utilities. We hope this guide empowers you to write more efficient C# code, understanding both the power and the responsibilities that come with these advanced features. Continue to explore and optimize your applications responsibly.